Hello everyone. So the first topic of today's discussion is the stagnation state. Stagnation state. First we'll understand what is the stagnation state. So stagnation state is defined as the state of a fluid obtained when it is isentropically decelerated to zero velocity state is referred as stagnation state. Whenever let's say we have two cases, first and then second. So whenever there is a flow and with this that flow will have some enthalpy associated with it, let's say h1, and it will have some velocity v1 square by 2. So when it is isentropically deaccelerated and becomes to zero velocity, it means whatever will be the enthalpies at second state plus v2 square by 2, so this velocity will become zero, and at this case this equation will convert h1 plus v1 square by 2 is equal to h2 naught, or we can say that it is the uh, stagnation state of the state 1, h naught 1, we can say. Fine. So graphically we can represent it by this figure. Let's say it is the entropy axis and it is the enthalpy axis. Okay, and let's say we have a state at pressure P1 here at enthalpy H1, and the second state we have at enthalpy, not second state, at this state the enthalpy is H1, and when we add V1 square by 2, let's say we have added V1 square by 2 in H1, then we are coming to this H naught 1. Okay, so we come at P naught 1, stagnation pressure. At stagnation state, all the properties are defined in terms of stagnation state. So at this point, the pressure is called stagnation pressure and temperature is called stagnation temperature. Okay, so we can say that the stagnation enthalpy H naught 1 can be written as H1 plus V1 square by 2. Fine. So now we will understand the difference between energy transformation and energy transfer. So first, let's see what is energy transformation. So energy transformation, as its name suggests, that here the energy is transforming its state. It is converting from a form to another form. That is called energy transformation. Like for example, we can see this in nozzle. In case of nozzle, the energy transformed from one state, let's say H1V1, to another state H2V2, and here the V2 is much greater than V1. So energy is transforming in kinetic energy, more towards the kinetic energy. Its enthalpy is converting in terms of kinetic energy. Okay, so for this nozzle case, if we will apply steady flow energy equation as a PE, so we'll apply like H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. From this equation, we can understand that when from the nozzle, because enthalpy is decreasing, so velocity is increasing, so its enthalpy is converting into the kinetic energy. Okay, and from here we can calculate that H2 minus H1, or we can say H1 minus H2 is equal to V2 square minus V1 square by 2. Whatever be the reduction of the enthalpy, that is converting into the kinetic energy. So simple. Fine. So the important point is here to understand is that how we can understand it graphically. Okay. Graphically, we'll try to understand. what is energy transformation. Okay, so let's say this is the entropy axis, this is the enthalpy axis, fine, and we have state, let's say T1. At H1 we have this state T1. At H1 the temperature will be T1. Okay, and the pressure will be P1. The pressure is P1. This is the first state. Now, as from this nozzle case, we'll draw. I mean, we'll try to understand in case of the in case of the in terms of the graphical representation. We'll try to understand this nozzle case, that how the energy is transforming. So first of all, this is the first case. This is the second. Okay, we'll understand in terms of the stagnation states and how the energy is transforming. So this is our first state, fine. And from when it is coming from first state to second state, so we are knowing that here the enthalpy is decreasing. H1 to H2, H2 is less, so it is coming to another state H2, which is less than H1 at temperature T2 and corresponding pressure P2. Okay, so enthalpy is decreasing. Now, now the thing is to understand that now from this equation, this term we can define as H naught 1 stagnation state at section 1, and this term stagnation state at section 2. Let's say that the section 1 state we have decelerated and it becomes to zero velocity state. So at that state the enthalpy becomes stagnation state. Right? Now we'll try to represent that stagnation state in this graph. So from state 1, this is state 2. From state 1, when it is coming stagnation state 1, H naught 1, so it wants some kinetic energy that will be V1 square by 2. It wants, then it will become H naught 1. And for the case of 2, it want H2 V2. Let's say will represent here V2 square by 2. This one when will add, then it will become H naught 2. So stagnation state will be same, and the pressure corresponding to this state will be P naught 1, which is equal to P naught 2. Stagnation pressure will be same, and also temperature, you can see T naught 1 is equal to T naught 2. Temperature is also same, but here keep in mind that nozzle is adiabatic. We have assumed that nozzle is adiabatic, so there is no heat transfer. That's why the stagnation pressure is same. Stagnation temperature is also same. Otherwise, we'll see in other cases that what can be the differences. So here we can see that enthalpy is decreasing, and that's why here we can see that velocity increases. Velocity increases. Fine. So this is the case of energy transformation, where this energy is transformed into here in case of increasing velocity, but stagnation state remains same. Okay. So now we'll try to understand what is energy transfer. So in this case, energy transformation, we have seen that the energy is transforming from a state to some another state, or in a form to from a form to some other form. But in case of energy transfer, what is energy transfer? So in case of energy transfer, the energy will transfer from a state to somewhere else. Energy will transfer actually. I mean, let's say we have assumed a system and there is some energies associated with this system, but what will happen that some amount of energy will get transferred somewhere else. Let's say we are transferring work as a work to somewhere else. So that is the case of energy transfer. I mean, so if you want to see the examples, then many examples will be there, like turbines, turbines, IC engines, whatever is delivering some energy or work, like these devices are energy transferring devices. So let's say we are, if we want to understand in case of compressor, so here this is state 1 and this is state 2. Here enthalpy is H1, state P1, H2 and pressure P2. Fine. Here what we know that pressure P2 is greater than P1 because compression increases the pressure and velocity becomes approximately same. There is not any change in velocity. Compressor is more concerned towards the pressure, increase of pressure. So if you'll apply SFE, steady flow energy equation in state 1 and 2, because energy will remain conserved. So here H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. But what will happen that here this H1 plus V2 square by 2 will be more because pressure energy is increasing. So it is not balanced. So what compressor does that we have to apply more work. So we need to subtract here compressor work. Then this will balance. Okay, so what we can say that here the stagnation enthalpy at state 1 is equal to stagnation enthalpy state 2 minus compressor work. So how we are getting the compressor work? We are getting the compressor work, not we are getting, we are delivering the compressor work is equal to H naught. Okay, compressor work we are delivering with, okay, H naught 2 minus H naught 1. Fine. We are delivering the compressor work like this. I mean, this is the positive compressor work we are saying. But what is happening? Actually, compressor work is negative. So H naught 1 minus H naught 2 because the final state is more and initial stagnation state is less. So this will come out to be negative. Okay, because the here that's why it is called the energy transfer because energy is transferring, not energy is converting from stagnation state 1 to stagnation state 2. We'll try to understand it in the graphical manner. Okay, so let's draw it. Enthalpy versus entropy, and we'll try to understand it clearly. Fine. So as we have the state 1 at pressure P1 and temperature T1 at enthalpy H1. Okay, and we are going to from state 1 to state 2. Let's say we came here at state 2, H2. Now, why here enthalpy is more, H2 is more? Because we are applying work, we are delivering work. Because of delivering work, the energy of the final state will be more. Okay, so that at state 2 we'll have pressure 2 and temperature 2. Now we'll try to understand with respect to stagnation states. So for the case of one, if you want to find out the stagnation state, so we'll add some velocity. Let's say v1 square by 2 we have added, and we come to stagnation state h naught 1. Fine, and here the pressure will be p naught 1. And from the point 2, if we'll draw the stagnation state 2, so we'll add v2 square by 2 and we'll come to stagnation state 2. Okay, and the stagnation pressure will be P naught 2 and T naught 2. T naught 1. Okay, fine. So what we are seeing here that the difference of H naught 1 and H naught 2, H naught 2 minus H naught 2 is nothing but the compressor work. This is the compressor work. What we are delivering. So important point to note here that the stagnation point work as the reference point to denote the total energy content of the fluid. I'm repeating again that the stagnation point work as the reference point to denote the total energy content of the fluid. Stagnation enthalpy always remains constant for energy transformation. Okay, this is not the case of energy transformation. Here the energy is transferring because it is the compressor from a state to another state. We are transferring the energy. Okay, so the stagnation state will not be constant. Here we can't say that H naught 1 is equal to H naught 2. Okay, so for the case of energy transfer only, H naught 1 is equal to H naught 2. Okay, but for the case of energy transfer, we can't say. So for the case, all the cases for the energy transfer, the stagnation states are not constant. Okay. Okay, and the second point is that for energy transfer, stagnation enthalpy increases for compression and decreases for turbine. Yes, of course. Like in this case, for the case of compressor, we have seen that the stagnation state is increasing, and if we draw for the case of turbine, then we know that the enthalpy will get decreased. You can draw and see. Okay, fine. Thank you. Thank you very much.